All right, we're going to get started for today. Welcome everybody again to this Innovation Showcase Summer Series, a collaboration between the Ontario Water Consortium and Dynamita North America. And this one's entitled From Digital Models to Digital Twins, Developing Solutions for the One Water Industry. Before we proceed with the webinar, I just want to talk a little bit about the consortium and what we do and why we're here. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together water researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, supported or created more than 350 industry jobs, and advanced nearly 80 water technology projects. We've partnered with over 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before introducing you to today's webinar, we also hope you'll join us for our final summer webinar. On July 14th, Bishop Water will present on decentralized low energy solutions for managing biosolids and nutrients ideal for small and rural communities. I will drop the registration link in the chat in just a moment. All sessions are free to join. Please also note the QR code you can use here to subscribe to the OWC newsletter to stay up to date on all of our news and programs and opportunities. Now, I'm very pleased to hand it over to Tanush Wadhawan, Director at Dynamita North America, to begin today's webinar, again entitled From Digital Models to Digital Twins, Developing Solutions for the One Water Industry. Oh, Tanush. Okay.
Great. You guys can hear me?
Yes, we can hear you.
Okay.
The floor is yours, Tanush.
Thank you, Robert. Thank you, Robert and Rahim, for this opportunity. So today my goal would be to tell you guys about what we do and talk about how we've been moving from developing software for digital models to digital twins. I want to introduce my team and what we do. So we develop process modeling software for water and wastewater treatment. And our team is basically composed of, mainly process engineers and programmers working together to build a solution which works for the industry. We essentially have 4 products we've been working on. Sumo, which has been commercially released into the market for more than a decade, is being used worldwide. It's mainly for simulating wastewater treatment processes. You can do greenhouse gas emissions in the advanced form, or you can actually simply do BOD removal, nitrification, denitrification. So it covers all the aspects of a wastewater treatment plant. Sumo later is a digital twin toolkit, which allows you to connect your real plant data with the simulator, which is Sumo, and do real-time simulations to understand the performance of your plant. The third product which we've been working on, and we haven't commercially released it, but a lot of utilities and consultants are doing a beta trial. Dynamita is a software which will be focusing on water treatment. So it will focus on drinking water. It will focus on municipal reuse water treatment. It will focus on industrial process water applications such as pure water, ultra pure water. And finally, a new product we've been working on is Cassandra. It's an AI influent forecaster in which you can train the software or train the machine learning algorithms using your influent data from your plant, and then use it to predict flow into the future. And then all of these can be connected to each other to get the best of one water solution. So in Sumo, you can put together a complete wastewater treatment plant configuration. This here, what you see is a A2O process with internal recycle. You have blowers for energy calculations. The primary clarifier is sending sludge into a fermenter. There is a P release tank. Then there is anaerobic digestion, which can be simulated. You can do gas emission calculations and energy calculations from combined heat and power units. We also have precipitation, so you can focus on resource recovery as well. So Sumo is a comprehensive software which allows you to simulate different process applications, different operational strategies for your plants, and identify how your technology fits into this plant. Dynamita, on the other hand, focuses on, like I said, reuse application. So it's more focusing on using membrane technology such as ultrafiltration membrane. It uses reverse osmosis. It has units such as decarbonator and ultraviolet AOP, advanced oxidation processes, to be able to simulate the water treatment side of the business. Now, coming to Sumolator, what is Sumolator? A Sumolator allows you to connect your utility, the data you've been collecting in the SCADA system, to a live model, which is running in Sumo. So essentially, you'll prepare a configuration or a configuration of your plant in Sumo, and then you can connect it to the data of your facility. The first step which comes into play is called monitoring twin. So you try to represent the real live operation of your facility in a digital model. And that's what a monitoring twin is. The monitoring twin is working side by side the plant and receiving data from the plant and sending feedback to the plant in terms of what kind of operational information you might want to gather from the model itself. The second part of the digital twin application is optimization. So you can use the monitoring twin which you have created, which is working side by side your facility, and then you can optimize to identify best operational condition. And that requires not only knowing what your plant is doing right now, but also feeding in information using an AI influent predictor so that you can identify operational set points into the future. And that information then can be sent back to the monitoring twin, which can be relayed back to the SCADA system, and then the operators can decide if they want to include those operational changes into their operation or not. So one of the case studies we've been working on is the Hampton Roads Sanitary District in Virginia Beach. The facility is Nansmond, a wastewater treatment plant with over 900,000 cubic meter per day of wastewater, raw wastewater to be treated in their 5-stage BNR process. And one of the goals is to use digital twin and use the model to identify the DO set points which result in a tighter ammonia control around their set point. So what we have done for HRSD is we have connected a digital model to their SCADA system. So from their SCADA system, the data gets cleaned and sent through a Python script or a digital control script into their process configuration in Sumo. This file is running in real time, meaning that the data is coming in very frequently. So every couple of minutes or every 5 minutes, however anybody wants to set it up. The calibrated file is then auto-calibrated every week. The model file is auto-calibrated every week. We do sensitivity analysis on a weekly basis to identify the correct SRT and waste rate. Now, this acts as a monitoring twin. On top of the monitoring twin, we get the mixed liquor composition from the monitoring twin and send it to a smaller file where we identify what the DO set point should be so that the plant can operate at the ammonia set point they desire. So the mixed liquor composition is then sent through the Python script into a smaller Sumo file, which also receives the ammonia information or the ammonia load information from the future, meaning that the predictor is predicting what the ammonia concentration or the ammonia load to the plant will be every 20 minutes, 2 hours into the future. And that information is relayed into in a Sumo file where the optimization is done. And the DO set points, which are identified, are sent back to the SCADA system. And this allows them to use the model and create a digital twin application where they are trying to control the ammonia set point closer, the ammonia in their effluent closer to the set point they have in their mind. And in this graph, you can see, if you pay attention to the primary y-axis, the ammonia concentration changes from 0.2 to maybe 5 milligram nitrogen per liter. And these variations around a set point, which is the black line, you can see that the variations are quite high. And at this point, we have implemented this digital twin application. And you can see after the digital twin application comes into play, the ammonia in the effluent is much tightly controlled around the ammonia set point. And if we zoom into one of the smaller phases of this operation, you can see the variation before and after the digital twin application has been implemented. So before the digital twin application has been implemented, signified by these hollow squares, the variation of ammonia around the set point is quite high. While after this digital twin has been implemented, the control on the ammonia in the effluent is much tighter and around the set point. So this is one of the applications where we are moving our digital models into digital twin applications. So if you ever want to test out any of these products, all you have to do is write to us and we can give you a free trial license to use it. Okay. At this point, what I'll do is I'll actually go over to Sumo and show you the interface and talk through how we can build a plant together. So I'm going to go over to Sumo and I'm going to pick one of the examples. So in the home page, you can see that on the left-hand side, there is documentation which you can view. And on the right-hand bottom side, we have a bunch of different examples we can choose from. And today I'm going to choose the MLE example. So once you open this example, it will take you to the configure page. In the configure page, this is where you'll actually put your plant together. So in this case, we have raw influent going into the primary clarifier, followed by an anoxic tank, and then an aerobic tank with internal recycle represented by this side flow divider. Then the sludge flows into a secondary clarifier. The underflow of the secondary clarifier goes back to the head of the anoxic reactor before it's wasted. And this allows us to control the sludge retention time. Okay, so this is a simple configuration for total nitrogen removal for a BNR process. When we go to the model tab, in this tab, we are able to select different type of model options. So we have one-step nitrification, denitrification, full plant model, and a two-step nitrification, denitrification, full plant model. And the difference between the two is, in the one step, we have ammonia biologically converted to nitrate, while in two step, we have ammonia going to nitrite, and then nitrite goes to nitrate. And the advantage of using two-step is whenever you're doing deammonification in side stream, or if you're looking at shortcut nitrogen, or if you're doing pDNA, partial denitrification with NMOS, that is the model you can select to do BNR treatment. We also have models which focus on sulfur biology and chemistry. We also have a model which is dedicated to greenhouse gas emissions. So you can select these different model options and identify what's the best option for you. We can look at gas transfer calculations, the off-gas emissions of the composition of the off-gas. You can use pH in your calculation. You can calculate pH and predict the impact of pH on your nitrification process. You can look at precipitation, such as struvite or vivianite formation in your digesters if you add iron. And then one of the new features we have recently added is PFAS. So you can actually model PFAS from the influent and understand how it transports through your facility and how much of it can end up in your sludge. In the same tab, you can look at some of the kinetic parameters or stoichiometric parameters, which are right there, here at the bottom. And in order for you to calibrate your plant, you can look to these kinetic parameters or stoichiometric parameters and decide which one works best under which scenario. Although all of these parameters have been identified over the years of research, years of experience with working with many different utilities, and hundreds of years of experience we have in activated sludge systems. When I go over to the tool tab, in the tool tab, you're able to calculate the sludge retention time. So you can create a calculation where you can drag and drop units from your configuration and simply create a calculation you require. So in this case, we are looking at sludge retention time. And in sludge retention time, we are calculating the mass of solids which are sitting in these two tanks divided by mass of solids which are leaving in the waste stage and in the effluent of this plant. You can similarly calculate the hydraulic retention time. You can do proportional flow dependency. So for instance, the RAS flow is sometimes said to be proportional to the influent, and that can be done using this feature. We also have controllers which are part of the configuration, also part of the package. So you can look at continuous P controller, deadband controller, PID controller, and so on. If I go to the input tab, in the input tab, you can define constant values if you click on the influent, such as the flow rate, COD concentration, DKN for the influent. If you switch over to your primary clarifier, you can provide information which is necessary for you to simulate regarding a primary clarifier, and so on for your CSTRs, for example, for your tanks, and then secondary clarifier. The SRT calculation, which is part of the tools which we created, if you click on this button on the drawing board, you can actually provide an input SRT and the model can calculate what the waste stage should be. So model can allow you to maintain the SRT by identifying the correct sludge retention time. And you can do this by simply turning on the waste stage SRT controller by turning it into true and providing a value which you would like this plant to operate at. So let's say if we want to operate at 10 days of sludge retention time, we would simply enter 10. And now we can go to the output and see what the results would be. So in the output tab, we are able to create these different tables, time charts, XY chart, to look at many different concentrations and composition of your wastewater. And you can simply do this by dragging and dropping any of the parameters. So if I wanted to recreate this table, all I have to do is click on table, click on influent, and drag the frequently used variable to the right. And you can see that it populates itself different composition of wastewater in the influent. Now you can drag any of the process units. So you can drag your anoxic tank, and the information is populated, which is, of course, pertaining to that anoxic tank. Then you can do aerobic tank, and then you can drag and drop your effluent as well. Okay. You can similarly create a time chart where, in this case, we are looking at the effluent total nitrogen, ammonia, and nitrate and nitrite. Let's go to the simulate tab. In the simulate tab, you have option of doing steady state calculation, or you can do a dynamic simulation. So if you do a steady state calculation, which is this button, the simulation is done almost. You can see these blips, and these results tell you what the steady state values are for your plant's performance. We can go to the table which we have created and look at, let's say, the ammonia concentration. So the ammonia concentration in the effluent of this plant at steady state is 0.5 milligram nitrogen per liter. Right. Now, what if we wanted to evaluate two different conditions? If we wanted to see what happens if the plant configuration and the operation remains the same and the temperature of the influent is lower. So to simulate the winter condition, if we go to the input, we can click on the influent, and we can either change the value of your temperature in the influent from, let's say, 20 degrees to 10 degrees right here, or we can select it as an advanced parameter. And once you select it as an advanced parameter, you no longer can change that temperature value from this input tab, but you can go to the simulate tab, and you can see that this value appears right here. And now you can change the value. So you can double click here and change the name of the scenario to winter, and change this to, let's say, 8 degrees Celsius, and perform another steady state. And now you can see that the ammonia concentration is 3.8 milligram nitrogen per liter. Okay, what if you wanted to do more than one scenario evaluation? You can click on this plus button and then create another scenario. So in this case, because the default temperature is 20 degrees, let me call it an annual average. And I would add another scenario, which I would call summer. And I will make this 25 degrees Celsius. Okay, so I can uncheck the winter and check the annual average, or I can uncheck the annual average and check the summer and redo the simulation, or I can actually select all the three scenarios and perform a steady state calculation. So if I press steady state, after I've checked all three, Sumo will actually do simulations for all three scenarios and allow you to see them from one graphical user interface. So I can actually go from, let me right click on this header of the frequently used variable table, select a scenario. You can see the summer scenario is showing that the ammonia and the effluent is 0.36. If I go to the annual average, you can see it's 0.55. If I go to the winter, then it's 3.8. So you can create multiple scenarios and evaluate them at the same time by doing just one click. if I go over to the time chart and look at the effluent nitrogen, of course, we did steady state calculations. So that means there is no relation to time in this case. And that's why you see these blips. Okay, what if I do a 1-day dynamic simulation and I combine the steady state with the dynamic simulation? So I press steady state and dynamic. And now you can see results from all the 3 simulations which we have set up on one single time chart. And this allows you to understand the impact of the operational changes, of the variability in your influent on the impact of the performance of your plant. And we can narrow down to look at just the ammonia. Of course, you can highlight with your mouse and see, okay, this is the winter condition, this is the annual average, and that's the summer condition. Okay. Now, this is one way for you to identify or understand the impact of the temperature. Now, one of the common things we like to do when we are looking at designing a plant is to identify what the minimum SRT of this process is. And the minimum SRT is the lowest SRT at which you achieve your desired effluent quality for ammonia target, meeting your ammonia target at the lowest temperature. So there is another feature in Sumo where we can evaluate not just 3, but a range of values and plot those values on an XY chart and look at how the ammonia concentration is changing as the SRT changes. Okay, so for this second simulation, what I'm going to do is I'm going to go back to the input. I'm going to click on the sludge retention time, and I'm going to select this SRT as a parameter which I will modify. When I come back to the simulate, you can see that the SRT shows up in the advanced window. I make this change by going from simulate to advanced, and then I can choose the winter scenario. So in winter scenario, it's 8 degrees Celsius. That's the lowest temperature for this plant. I would select the sludge retention time as a parameter which I want to evaluate. And I would change the SRT from 2 days to, let's say, 10 days. So that's my minimum SRT, that's my maximum SRT, and I want to do 10 simulations between them. Okay, so from 2 to 8, 2 to 10, the first simulation will be at 2 days of SRT, the last simulation will be at 10 days of SRT. And I'm doing 10 simulations between them. And if I do a steady state, this time chart will automatically convert into an XY chart, and you would see the impact of your SRT on the effluent ammonia. So you can see that at 8 degrees Celsius, even if we increase the SRT to 10 days, at 10-day SRT, you reach 3.8 milligram nitrogen per liter of ammonia. Okay, we can extend this from 10 days to 15 and still do 10 or more simulations if we wanted to, and redo this. And Sumo is doing 10 simulations. And now you can see that if you want to achieve a minimum SRT, or if you want to achieve a target ammonia in your effluent, let's say, of less than 2 milligram nitrogen per liter, then you must maintain the SRT for this plant at 8 degrees Celsius at 14 days of SRT. So that's the minimum SRT at which you can achieve your 2 milligram nitrogen per liter or less ammonia target in your effluent. So these two are simple ways of evaluating or using simulators to do an evaluation of your facility, identify operational set points. Now, you can use this and convert it into a digital twin model, which is connected to the plant, where the influent is receiving from the SCADA the actual flow rate, the actual COD, the actual TKN they measure, the actual temperature they're measuring in the plant, and the model is being used to identify what is the SRT they should be operating at so that they can meet that effluent ammonia target. And once you're done with this evaluation, you can actually create a report. So if I create this report by clicking on this button right here, it will allow me to open an Excel file, save and open an Excel file. I'll say, yes, I want to open it. And in this Excel file, you'll get all the information. So you have information regarding the plant configuration. You have information regarding what was the SRT, the number of simulations which were performed. Let me see why. Okay, performed. And then you can also get values for each of the simulation, the final values for each of the simulation. You can get all the information which you have set up in your Sumo, and all of those simulations will show up. So for example, this is at 4.9 days of SRT. And if you scroll down, this will be at 14 days of SRT. And then you can create your own graph if you wanted to understand the performance. All right, so those are the key aspects of Sumo, which I would like you guys to know. But apart from that, we have a model which can do energy calculation, you can do cost calculation, you can do carbon footprint calculations as well, scope 1, scope 2. You can optimize, you can use it for design. So you can ask Sumo to tell you what the reactor size should be to meet a particular criteria. You can identify different operational set points or optimize for operational set points and so on. Okay, so like I said, guys, visit us at dynamita.com, write to us at support@dynamita.com, and feel free to download Sumo and write to me if you have any questions and get a free trial license if you need.
Thank you, Tanush, for that presentation and your demonstration. We'll now move to the question and answer and feedback component of the webinar, and there's already a few of them in the Q&A. The first one is, there looks like to be about 4 or 5 questions at once, but we'll take them one by one, Tanush, and I'll read them out loud so everybody can hear them, and then you can go ahead and answer it. So these are questions from Jonathan Ross, and Jonathan Ross asks, what data do I need to get to use the influent forecast tool? How reliable has it shown to be? So we'll start with that.
So for the influent forecast tool, what we've been looking at is there are different algorithms which we have put together, and influent flow rate obviously is the most important one if you want to train the data, if you want to train the model. So you need influent flow rate, you need weather data, so the temperature of your wastewater or the ambient temperature, the precipitation going on for your utility, and we need at least a couple of years of data in the past to be able to train that model. And once you have trained the model, then what you need is access to what your temperature is next week. And the model should be able to predict that, okay, this is what your flow rate should be next week. If next week you're looking to predict flow on a Wednesday at 10 a.m., when this is the precipitation and temperature, what it looks like. And the results vary from plants to plants. Some plants I've seen work very well in predicting what their influence should be, while for others it's not so easy, because what you're trying to do is you're trying to capture the whole watershed. And sometimes it's not that straightforward. So you have to look at the watershed and the precipitation, the type of data which is available. But essentially, you're looking at weather data and the influent flow rate, and you can train the model. And what I've seen is minimum of 3 years of data allows you to train the models in such a way that you get reasonable results out of it. And this is hourly flow rate data. So 3 years of hourly flow rate data with temperature and some weather conditions included.
Okay, thank you very much, Tanush. The second part of Jonathan's questions are, what are the installation requirements for the digital twin toolkit? Describe in short how I'd go about using it to connect to my plant. What do I do?
Yeah, so it depends on how you want to set it up. So in case of when we were looking at HRSD, they wanted to be the digital twin on one computer inside their server. Okay, of course there are cloud applications as well, but because of security risks, sometimes it's easier for utilities to do it inside on a single computer inside their own server. And what you need is, you need a Sumo license, you need a digital twin license, and then you need a calibrated plant. And once you have a calibrated plant model, and once you have a calibrated plant model, you can identify what information you need to send from your SCADA into the plant model file. So most frequently, of course, you want to send in your flow data, you want to send in temperature data, you want to send in TKN or COD measurements which you're doing. And of course, COD measurement is not something which you do on an hourly basis. So you can decide on the frequency of how frequent the twin will receive the data from your SCADA system, and then set it up. So essentially, you need a calibrated model file. You need license for that Sumo. You need a digital twin license, and then a Python script which allows you to send data from one file to the other. And that's pretty much it.
Great, thanks, Tanush. Third part of the question is, your twin pushes set points to plant. How does it protect my plant data and IT infrastructure?
Sorry, can you repeat the question, Robin?
Sorry, yes. Your twin pushes set points to plant. It's a question.
Yeah.
How does it protect my plant data and IT infrastructure?
Yes, so good question, actually. We don't necessarily promote sending, so it's an option. And I've maybe seen one application where they're actually sending data back and setting things in the SCADA, while in 99% of the applications, the model is just predicting, okay, this is what the operator should be doing, and that information is available to the engineers and operators to evaluate and see, okay, should I be making those changes or not, right? So it's supporting the operations rather than just taking over and changing the set points directly in the SCADA system. Yeah. So in 99% of the applications, you can actually, of course, you'll set up that the information doesn't go back to your SCADA system and doesn't change the set point itself. Although it's possible to do, but of course, it depends on how reliable your twin becomes. And that takes time. So it might be years before you can decide, or months in case of HRSD, to decide, okay, I'm comfortable with this model, I'm comfortable with the twin predicting over last year that I can allow it to change the set point without having an operator, reviewing it. But 99% of the cases, we don't send it back. You don't want to send it back. You want the operators to just learn from it and then make a choice, if that makes sense.
Right.
And like I said, because the twin is implemented inside your server and SCADA system, there is no threat from outside. We don't have any. Once the twin is set up, Dynamita or no one else has any information regarding your own twin. Only you have access to your own twin. Nobody else. It's not connected to the cloud at all.
Excellent. The last part is, how exactly is the monitoring twin set up? What can it monitor and for how long?
Yeah. So essentially, a monitoring twin, when we switch it on, we are switching it on to work in real time with the plant, and it can go on for years and years without rebooting it. If the system crashes, it comes back on and then it continues. What can it monitor? The whole idea is, so the exercise which I did right now, I did it manually. right? I manually changed the temperature. I manually evaluated what the SRT should be. Now, you will hire a consultant to do this and identify what the operational set points should be, maybe once a year, or identify or use a consultant to do a simulation to identify, create a calibrated model and identify what would happen if my flow is double. But imagine automating these tasks. And that would mean that you have reduced the frequency of simulating these scenarios on a regular basis. So maybe not a month, maybe not a year, not a month, maybe a week, maybe every day you can evaluate these scenarios, right? And that's the information which an engineer will tell you manually is what you can gather automatically, which you can automate. So all the information you can think of as an engineer, okay, a model will tell me what is my iron dose. Yes, you can use the model and automate it into a digital twin, and it can tell you, okay, if your phosphorus load is this much in your influent, then this is the iron load you should be adding to your system.
Thank you, Tanush. And Zamina, I apologize. I only just noticed that your question came in technically a minute earlier than Jonathan's questions, but we'll get to them now. So Zamina asks, how much water consumption, if any, do these models use? I.e., has sustainable water consumption been considered in deploying these models?
Yeah, so we are not using, the application which I just shared, like I said, is on one computer and one server. It's not an AI model like large language model where it can, it needs to run in a data center and consume a lot of water. This is running on your laptop. It could be running it out of your laptop. So whatever your laptop's energy demand is, that's all it's consuming, right? If you want to convert it into how much hydro it's using, that's different. But it's I would say not a lot. It ends up saving you a lot of energy costs, actually.
And so now we still open the floor to anybody else to either post their questions in the Q&A, or you're also able to raise your hand if you want, and I can unmute you if you want to speak directly to Tanush. We're also happy to do that. If you have any further questions for Tanush, of course, you can also follow up with him with any questions, or if you're interested in testing the system. But now's your chance. Please put any of your questions in the Q&A and or raise your hand, and I will then unmute you. And there's Zamina. And let me allow your mic. Zamina, the floor is yours.
Thank you so much. Yeah, and thanks for answering the earlier question. Yeah, I was curious whether it was an LLM model, so that's good to know. The other question I had was related to the case study you presented with the sanitation district, and I was curious whether you faced any sort of barriers to be able to deploy your model in the first place, and yeah, what were those barriers, and how did you kind of overcome them?
Yeah, good. So there are always barriers when we are when we are trying to deal with IT people at utilities, because they, like somebody was asking about security concerns, there are always security concerns. So that was the main barrier, where we wanted to send information from the SCADA system into this particular computer, which was already on their server, and into Sumo. And we overcome that by explaining to the utility that the model is inside and no data is going into any cloud and not being stored on with us. It's actually everything is with you. It's like a desktop application. So it's like a Word file. When you open a Word file, it's not that the Word file is available to everyone in Microsoft. It's only available to you and your organization. So that was the key concern which we addressed. The other things which we looked at was like I explained, flow rate information is much more available, right? You can get flow rate, influent flow rate every hour, while COD is not something which you can get every hour unless you have a sensor which is measuring COD. So how do you get COD measurement into the model correctly? Because imagine sampling today for doing a composite sample, taking the sample to the lab does COD measurement. It already is 24 hours plus 2 hours of measurement, and then another maybe 15 minutes of that data showing up in your SCADA system, right? So the data is already delayed. So how do you manage that? And there are different ways of doing it. There is that you can let whatever the last data is define your COD for the next whole day, or you can create a relationship between temperature and COD, like a soft sensor, and then recorrect the model if you need to, kind of thing, right? So those were the, I guess, two main challenges. Third was the system would crash. Let's say if somebody would close it by accidentally, not necessarily crash, but if somebody closes it accidentally, then what happens? In this infrastructure, you have to understand is that data is generated. There is a time lag. So when the data is generated, Sumo needs to get the data at that time as well, right? So the overhead needs to be very little. So what if somebody turns off Sumo? So how does it start? So we prepared a wrapper or a program which would automatically restart that connection between the SCADA and the software and continue. So those were some of the few challenges, I guess.
Are there any further questions? Again, you're welcome to them in the Q&A. I think I see another one. There's a few more questions that came through in the Q&A. So let's just see. Jonathan Ross said, please show how I can connect a model to the plant. I mean, perhaps you can, Jonathan, you can also reach out directly to Tanush and discuss that. Zeng says, how do you deal with the flow's concentration forecasting?
How do you deal with?
How do you deal with flow's concentration forecasting?
Yeah. Okay. So good question again. So I mean, you can train. Of course, you can train the AI model to different concentrations if you have those measurements. But instead of training a model, I would say just using like a regression and understanding relationship between flow and concentration and flow and temperature is enough for you to set it up. The other option is, I mean, there are two more options. One is actually using a sensor. The other option is to create a soft sensor out of your. Oh no, not so soft sensor. I already talked about. So you can have a sensor. You can have a soft sensor like a regression, or you can actually do a sampling campaign and get a diurnal pattern of your COD, and then apply that based on flow to your model, and that would be okay as well. You know, for digital twins, the application is the monitoring twin might seem general, but the optimization and what you really want to do with the monitoring becomes very, very important to identify for your facility. So in their case, HRSD case, they were interested in ammonia. I'm working on another plant that is interested in predicting iron for their facility. And then there is another plant who just wants to do wastage and identify something very simple, or try identify what the underflow of your primary clarifier should be. So depending on those different applications, different things become important in the influent. And then you can decide to measure them and create a relationship or put a sensor. If you don't have a sensor, and if you don't have the budget for sensor, then the easiest thing to do is to look at past data and create a correlation and set that up in the model. And that should be okay too. I mean, it doesn't have to be, I won't say it doesn't have to be 100% right all the time, right? There is some leeway in how you can set this up.
Thanks, Tanush. And we're going to combine these two last questions from Jonathan together because I think they are fairly similar. Because what Jonathan asks is, so I need to program in Python to set up the twin. What if I'm not a programmer? And then he later asks, do I need to learn how to program to use this twin toolkit and fit my project needs? So the question is around programming requirements and skill.
Yeah, so we can actually, I mean, idea is that if you have a programmer or your IT people can actually, we can send you a sample script which you can look at and prepare your own twin. You can ask us to do it for you. And then there is always support, and we can support you. So if you have someone who is interested and wants to test it out and use Python, our programmers and engineers will actually support you, and that would be part of the package as well, right? But you can actually ask us to do a project as well, or ask a consultant to do a project, and they can use Sumo as well. So there are many different variations of how this can be achieved. And no, you don't have to keep using Python. There is always graphical user interface options which you can do. So in this case, Sumo will open up and you can see everything happening in Sumo. And if you need to change something, you can save the file again and restart the digital twin monitoring if needed. Right.
Excellent. There are no more questions in the Q&A. We are a little bit over time, but I think if there is anything final, please raise your hand and or write it in the Q&A section, and we will wait a little bit for that, but if not, we'll probably end the event shortly. So any final questions for Tanush, please add them to the Q&A and or raise your hand if you'd like to ask them directly. All right, I think that seems like a natural end to the webinar. I'd like to thank Tanush and Dynamita for presenting here today. Very interesting webinar, and I'd like to thank all of our attendees here for your interest, and we hope that you join us for future webinars as well. But Tanush, thank you very much today. Hope everybody found this interesting, and please do connect with Tanush on trying out Sumo, or if you have any other questions, please do reach out to Dynamita directly, or we can connect you as well. You can also direct to me, and I can connect you to Tanush, and you can work from there. Thank you, everybody, today for your attention, and have a great rest of your day.
Thank you.
Thank you.